Okay, let me go ahead and share my screen. And what we're going to be doing is we're going to be talking about Chapter 7. Chapter 7 is going to be talking about work. And we're going to look at a couple problems that pertain to work, um, specifically on an inclined plane. And we're going to have one where we're on a flat surface. So here's the problem. We have a grocery cart and the grocery cart has a mass of 16 kilograms, and it's going to be pushed at a constant speed up a ramp that's 12 degrees incline by a force F of P that acts at an angle of 17 degrees below the horizontal. So that's a lot to swallow. So let's take that sentence and see how that breaks down. So in this case, we are starting the block off here, and we're moving it a distance of 7.5 meters along the ramp. The ramp is inclined 12 degrees, and we'll come over here in just a second and we'll see how that is also 12 degrees. And we are also told that the pushing force acts at an angle of 17 degrees below the horizontal. So if you can see that yellow line there, or just use the ruled line markers on this virtual paper as a reference, this angle right here is at 17 degrees. All right, so our next sentence says that we're going to try and find the work done by each of the forces. So m's of g, that's the weight, the normal force, and that pushing force on the cart if the ramp is 7.5 meters long. All right, so here are all the forces. We have our normal force, which always acts perpendicular to the surface that it's in contact with. We have our pushing force, which acts, in this case, 17 degrees above. Um, it was stated to be given as 17 degrees below. So the red one here, let's put that one, yeah, we'll make that one a dotted line because we're going to decompose the pushing force into its X and Y components relative to a horizontal. So let's see, we have FP of X, which is going to go in that direction. And then we're going to need FP of Y, which is going to go in that direction. And let's make that one FPY. And the other one FP of X. So we'll break this out a little bit in just a second so that you can get a handle of all the forces that are going to be operating here. And let's make this just a little bit shorter because I want it to kind of line up with that red vector. And again, what we're given is these pieces, and what we're trying to find over here, the work done by each of those forces. Okay, so what we need to start off doing is we need to first decompose the FP of X. I'm sorry, the pushing force. Remember, it was pushing in a fashion 17 degrees below the horizontal. So imagine yourself actually pushing this cart. So maybe you're standing here and you're pushing the cart but your angle is sort of downward. In this case, it's 17 degrees below the horizontal. But the horizontal is not horizontal per se from the standpoint of where the block is. The block is already inclined 12 degrees. So that adds another level of complexity to this. Okay, so the first angle is going to come as a result of that 12 degrees of incline. And again, as I said, the yellow line serves as a reference. So here's our standard XY axis. And here's that 17 degrees of decline. Remember, the green line is kind of used as our reference. This is our standard XY axis. I like to call it X plus and X Y plus, so I know which direction positive is for me. Okay. So the next step is to resolve or decompose f of p into its x and y components. And because the force does not act along the xy axis or on our tilted xy axis, our x plus y plus axis, we need to decompose it into the forces as directed along these axes, x plus and y plus. So you can kind of see here these two forces, FP of x and FP of y. Those are the decompositions of F of P, this piece right here. This is the actual direction of the force, but in order for us to do the math, we have to decompose the vectors relative to x plus and y plus. All right, so if you're struggling with that, what you might want to do is you might want to kind of recreate a triangle so that you can see how FP of x and FP of y are relative to our axes. So what I suggest you do is you first need to know where each one of these directions are going. So here's FP of x. That's what we're really looking for. Here is FP. That's the actual direction of the force. And then here's FP of y. FP of x and FP of y are going to form that 90-degree angle. And so this angle in here is a result of that 12 degrees of incline, this 12 degrees of incline, and this 17 degrees of decline. And so the angle right in here makes up 29 degrees, right? And so now you should be able to decompose this vector using trig identities. I always like to start off with a basic function if I don't know which one I'm actually going to be solving for. So I'll just start off with a cosine. So cosine of 29 degrees is equal to the adjacent side. So the adjacent side would be my FP of x over the hypotenuse, and the hypotenuse would be FP. So that when I rearrange this formula, it looks like this. Okay, and then likewise for FP of y. So now only calculate the magnitudes of each vector. The direction will be accounted for in the summation. So only the directions, only the magnitudes. So now we're going to decompose the weight vector. And remember, the weight vector, in this case f of g, is always directed towards the bottom edge of your paper, perpendicular to the bottom edge of your paper. So the F force is right here. Okay. again, a helpful way of looking at this, um, of resolving this triangle, is to start with an angle within the triangle, specifically the right triangle. Begin using sines and cosines as a function. So some of these are a little tricky. Sometimes students think that x is always associated with cosine. Not necessarily true. So let's see what happens in this case. So in this case, um, the force that we're trying to resolve is this F of G force, because it does not line up with that green um, standard x plus y plus axis. So what we need to do again is um, there's our right triangle. There's the x component of it. It points down the ramp, and here is the y component. It works perpendicular to the ramp. And so in this case, if you notice, let's see, I started off using sine as my baseline function, sine of that angle or reference angle of 12 degrees. And so sine of 12 degrees happens to be, let's see, opposite over hypotenuse. So f of g, fg of x over fg. And so when we solved it, fg sine 12 degrees is equal to fg of x. And then likewise, fg of y is equal to fg cosine 12 degrees. So again, not always is x instantly associated with cosine, nor y associated with sine. So be careful. Make sure you're able to resolve those vectors. Okay. The other force is the normal force, but because the normal force acts in the same direction as our standard xy axis or x plus y plus axis, um, it does not need to be resolved. So the normal force is all ready to go. So here are the forces that we're really dealing with. And you notice that they all point in the x plus y plus direction. So summarizing again, Fp of x is decomposed and we get this value. I wouldn't worry so much about what its actual, what the actual numeric value for cosine 29 degrees is right now. And Fp of y is as such. The force of gravity, or the weight component in the x and the y direction, are given here and here, and the normal force is here. We're trying to figure out how much work is going to be done on each one of them. Now, we talked about this term called work, but we didn't go into any great details. So let's understand work is just basically a quantity of energy. And sorry for scrolling so much here. I was trying to get to a spot where I could write, but work, what we don't want to use probably is we don't want to use W for work. So you'll see me write out either the work component as such, but you won't see me write that as W, because it'll get confused with the weight vector. So you might want to just write it out. The units are in joules, and this is going to represent some form of energy. Okay, so in physics, units of energy are measured in joules. And so now what we'll do is we'll start summing each one of those pieces in the x and y direction. All right, so let's see. Let's get my laser out. So summing the forces in the x direction. So anything that had an I hat component to it, I'm going to put here. All right, keeping in mind that anything that is opposite of x plus is going to be negative. So if I jump back up here again, you can see that this component and this component all point in the along the x plus axis, where let's see, FG of x here points down the ramp, so we'll constitute that as negative. Now, let's go back before we come to this second part and why it goes to 0. Let's go back to what the problem read. The problem read that the cart is pushed at a constant speed. Okay, so a constant speed means that the velocity is 0. Sorry, means that the acceleration is 0. So constant speed implies acceleration in the x direction is 0. Okay, so that's why I set that piece and set that to 0. And then summing in the y direction, we get these three components, keeping in mind the normal force is also embedded in there. And so why is the acceleration in the y direction equal to 0? Well, if this block is moving along this ramp and it's moving in that direction, it is not accelerating in the y direction. All right, and then F of G is that force of gravity. So let's start building into this. So if F of G is 156.8, we can now start to substitute and see how some of this is going to play out. So if I look at that very first equation, now I can see that the force of the pushing is 37.3 newtons. I simply solved this equation. So now I should be able to solve for the normal force. So the normal force comes out to be, well, the force of gravity, we just figured that out, right? And then the pushing force, we just solved that as well. And so now I should be able to solve for the normal force. The normal force comes out to be 171 newtons. That's that upward pushing along the ramp. Okay. So how do we find the work? Okay, so we kind of jumped a little bit here in terms of setting this up, but to determine work, we're going to take the product of a couple of pieces. So the work, which is measured in joules, is going to be the force times the displacement times the angle between forces and the angle between the force in question and the displacement. So in other words, it'll be written as force times d times cosine of theta. And sometimes this d might be called an s. Okay. So each one of these forces is going to have their own their own separate amount of work that they're going to do. All right, so let's figure out the work done by gravity. The work done by gravity is going to be its force, which we calculated to be about 156 newtons, times its displacement. It moves, in this case, 7.5 meters. And now the angle between the force in question, which is force of gravity, and the displacement, excuse me, and the displacement vector, which is as such. Now that's the tricky one. So remember that the pushing force, or the displacement, sorry, was the ramp was 12 degrees above the horizontal. And so that angle right there was that 12 degrees. So by virtue of the ramp being inclined 12 degrees, we get um, this little angle here of 12 degrees. But relative to the weight, it is 102 degrees. Okay. And the angle that you choose between the weight or the force in question, in this case, the weight, and the displacement is always going to be between 0 and 180 degrees. It's going to be the lesser of the two. In other words, you don't want to choose this angle that goes in this direction. Would be what is that, 360 minus 102 degrees. What is that, 258 degrees? You don't want to choose that one. You choose the smaller of the two angles. And in this case, it would be that 102 degree angle. Okay. And so in this case, it looks like the work that's being done is negative. So negative about 245 joules. All right, we got to do this again. Now we're trying to figure out how much work the pushing force does. So again, same formula. So let's write it down. Should probably write it down several times. So it's work times the force in question. In this case, the force in question is that pushing force. So how much work does this person that's pushing, he or she is going up the ramp, but he or she is actually pushing sort of at a downward angle. Just imagine you're pushing a shopping cart, but the floor is inclined 12 degrees, which is pretty steep, obviously. So you got to do a lot of work. So it's that pushing force, which we just figured out to be about 37 newtons, times the displacement. We call that D, or actually we called it S in this problem, sorry, times the angle, the cosine of the angle. And maybe we should call it theta 1 so we don't get it mixed up. In this case, it's the angle between the displacement vector, which isn't going to change, and the force in question. The force in question is that pushing force, and it's downward 29 degrees relative to the displacement. So in this case, we do positive work of about 245 joules. Okay. So the second part of this is we're going to want to know how to do scalar products. And if you kind of notice here, the scalar product is very similar to, you'll see that it's very similar to our work formula, and that's what we're trying to get to here. It's some force times some displacement times the cosine of the angle between those two vectors. Okay, so some of you guys may know this also as the dot product. So if you hear either one, just know that they're one and the same if you're trying to look it up. All right, so here's our basic definition for the dot product or the scalar product. And let's go through each one of these. So A and B are going to be some vectors, just like we had a pushing force and a displacement vector, or the normal force and the displacement vector, or the weight and the displacement vector. We looked at each one of those. And it's going to be equal to the magnitude of each one of those. The magnitudes going to be used a little bit, but not as much as this next definition, times the cosine of the angle between those two vectors. Okay. But we also have a formula that says if we dot two vectors, we get, and we take the product of each one of their corresponding x values as such here, as well as their y values and their, that should be z, as well as their z values. We can also get a dot product value. Now, when we find dot products, we're going to get a scalar value. So a scalar is the result. And a scalar is, for us, in vector terms, is just basically some number, okay, as opposed to a vector. So if I write this, it is not equal to this. So this is a scalar, some numeric value. It's a quantity, a magnitude, some numeric value that doesn't um, uh, tell us a direction or a length for the most part. And here is a vector. So we'll see later on when we do cross products that we'll get vectors as a result. So in this case, our key formula is going to be that the dot product is going to be equal to this. Okay, so you might want to keep those two things in mind. So let's look at this problem. This is problem number 17 in your book, and problem number 18 actually. And it says, what is the dot product? And so they're kind of getting you used to the jargon here of these two vectors. So what is the dot or the scalar product? And so these are going to be the two vectors that were given, A and B. But this time the coefficients are variables. So our x component for A is 2x squared. Our y component is negative 4x, and our z component is 5. So that means this thing is changing over time, right? So the vector length changes depending on where you are. And that's a little bit vague to look at, and we're also in 3 space here. But don't get too wrapped up in that. Just understand that we're going to use that second equation that I gave you. So we're going to take the coefficient of each one of those two pieces. If you look here, we're looking at corresponding x components. We multiply them. We take corresponding y components, even though that there's an x in there, it's a y component. We take their products there, and also the z components. Okay, and in this case, the dot product turned out to be a variable. In this next case, in problem number 20, so in problem number 20, it says that you're going to calculate the angle between the vectors. So let's write that down. You want to look at your book as well, just to make sure. So calculate angle between vectors. Okay, so again, here are our two vectors, A and B. So you notice that they're in 3 space. That means if we were to actually draw this out, you can kind of think of this as the bottom of the floor. There's our XY axis, and Z would be going up the wall, if you will. Okay, and X and Y are usually um, setting on the floor in that manner. If you've worked with the right hand rule, you can always remember which direction Z is in its standard form. Okay, but this time we're asked to find the angle between the vectors. So that means we're going to have to use this formula here. So let's see how we can use that. So we're going to first find A dot B. So we're going to dot it just like we did the previous problem, and we should come up with a value of 17.6. You might want to pause the video to make sure that you're able to find the dot product of those two vectors given that formula. Okay, good. Now, the second part of this is we're going to find the magnitudes. Now, this is in 3 space. I've made it a little bit more complex so that you can do the easier problems. But to find the magnitude of a vector, again, I'm right here and right here. All you're going to do is take the sum of the squares and square root them. Okay, so in 2 space, you're probably used to that. But in 3 space, you may not be as um, comfortable with that. So if this were in 2 space, in other words, if this were just simply an axis as such, and the vector, I'm going to make up another vector, I'm going to call it C. And C look like, let's see, 8 I hat units and 4 J hat units. So it'd be 8 in that direction and 4 in that direction. And so the vector would terminate here and look something like that. And so if I ask you to find the length or the magnitude of the vector, it would be the sum of the squares square rooted. And so it would be, what's that, 64 and 16. So it would be the square root of 80. What's that, roughly about a little less than 9. I wouldn't worry too much about that. So here's an example of that in 2 space. And 3 space, same thing, a little bit harder to visualize, but you're going to do exactly the same thing, just add that Z or J hat component. So there are your magnitudes. Now, if you rearrange that above equation, remember you had, let's get my laser pointer. Remember you just had that over here. So all I did was I divided by the, actually I'll probably put it right here. Doesn't matter, it's just one big product. So I solve this for cosine theta, and then if I take the cosine inverse of this, I'll get theta. We now know the dot product, right? We did that by doing this up above. That was at 76.34. And on the bottom, we have those two magnitude pieces, A and B. And so when we plug that into our calculator, we get 44.01. So those are the key elements of chapter 7 that I'm expecting you to know. And that is the first half of chapter 7.